This is your lucky day. Just watch until the end of this video. I've got a special surprise just for you. And if you're new to my channel, please subscribe, put a like if you may, and also put a comment if you want. Don't forget to share with friends and family. This channel will groom you into a guru at this subject. Please feel free to allow your ears to hear what I have to say. And after the end of this video, I've got cool prizes that I'm distributing to my viewers and my subscribers. Don't miss out this cool opportunity. Let's get down to business, shall we? Now, we are looking at measurements, scalars, and vectors. This is the first topic in physics, IGC, SE, Cambridge, or O-level Zimsec. Now, there are objectives that you need to exhaust in this topic so that you can master everything there is about this topic. Anyway, the first objective is physical quantities, followed by basic and derived quantities, followed by SI units and their use, voltage, current, and resistance, scalar and vector examples, resultant vectors, and resultant forces. A physical quantity is best defined as anything that can be measured, e.g., length and time. There are two types of physical quantities, which include basic physical quantities and derived physical quantities. Basic physical quantities are the building blocks of derived physical quantities. They literally make up derived physical quantities, e.g., length and time. They make up what? Velocity. Now we look at derived physical quantities. These are physical quantities that can be made or can be expressed in the form of basic physical quantities, e.g., acceleration is equal to delta velocity over delta time. That small triangle is read out as delta and it means change in something. So delta velocity is change in velocity. This is where acceleration is the derived physical quantity. Delta velocity is a derived physical quantity as well, which is furthermore expressed as displacement, which is a basic physical quantity, divided by time, which is also another basic physical quantity. Delta time is a basic physical quantity as well. Hence now, I'm not going to go deep into this, but I just wanted to show you where we start from. But I'm going to relook at acceleration in the following examples. Hence, let's express the following in terms of their basic physical quantities. We've got velocity, acceleration, work, kinetic energy, and potential energy. Moving on to the next page. On this page, we are having answers for the first part, which is for velocity. And you need to be able to define velocity. Don't worry much about the greater part of velocity. At this point, you don't really get that deep into velocity. We'll get that deep when you get to kinematics. Now, velocity is defined as rate change in displacement. Hence, to say velocity is equal to displacement over time. Rate change simply means change in time, right? That's what it means. Rate change means change in time. Displacement is measured in meters. Hence, it always qualifies to be under the category for length. Hence, we say we can rewrite velocity being equal to length over time. But remember, length is measured in meters and time is measured in seconds. So it's more like we're saying meters divided by seconds. And eventually get the SI units being meters per second. Thus, velocity has length and time as its basic physical quantities. Acceleration. It is defined as a rate change in velocity and it is a derived physical quantity, by the way, just like velocity as well. So acceleration can be expressed as saying acceleration is equal to velocity over time. Now, velocity, we said that it is equal to length over time. Therefore, we can say meters per second. It's also fine for velocity. Now, we look at acceleration itself. We are saying that from the initial equation where we said acceleration is equal to velocity over time, we want to substitute where or what we have written on velocity. Remember, we said but velocity is equal to something else. You get the sense? So that something else is what we substitute into our velocity on the equation of acceleration. Therefore, finally, we say acceleration is equal to length over time all over time. But length and time are and measured in meters and seconds respectively. So it's more of like we're saying meters divided by time divided by time, or meters divided by seconds, which eventually is the same as saying length over time squared. On the other half of this page, we are saying that length and time are the basic physical quantities of acceleration, and then the SI unit is simply length over time squared, or meters over seconds squared. So it's meters per square centimeters. Meters per square seconds. Work is the product of resultant force F and displacement. Work is therefore expressed as F times S, where F is the resultant force and S is the displacement. But according to Newton's second law of motion, F, the resultant force, is equal to mass times acceleration always. You have to bear this in mind. And do not worry much, we are going to look at Newton's second law of motion when we are looking at kinematics. Now, what do we do with what Newton has said? We simply take what he has said and substitute in our equation, our initial equation, which was saying work is equal to force times resulting force times displacement. So in place of F, we now put mass times acceleration, right? So work is equal to mass times acceleration multiplied by displacement. But mass is already a basic physical quantity, so you don't have to worry much about it. But for acceleration now and displacement, there's no problem. But acceleration now, it is a derived physical quantity. We need to reduce it again to its basic physical quantities before we can assume anything out of work. So we're saying, but acceleration is equal to length over time, and displacement is simply length. Therefore, work is equal to mass times the length over time squared multiplied by length. So work has length, time, and mass as its basic physical quantities, but we need to express it in the form of its basic SI units, right? So moving on, work is equal to kg. These are now units. Kg for mass, multiplied by m for length or displacement, over a squared for time, multiplied by m for length or displacement as well. So finally, we've got kg m squared s to the power of -2, or kgm squared over s squared. I move on to the next page. On this page now, we are saying that work has got its own SI unit, and very often at times people make that mistake of leaving it in the form of kgm squared s -2. You are correct, but on a half basis, you are saying that kgm squared s -2 is the SI unit, but it is actually the basic physical quantities that you have just shown there. We need the actual SI units. What is the agreed SI unit for work? And in this case, it's always 1 joule, or joules, right? Ke, that's kinetic energy, is the energy found in moving objects. Hence, kinetic energy is equal to half mv squared. You don't have to worry much about this equation, for it is always given in your physics data booklet, or even in your notes. You find it anywhere in any examination, it is there. But out of curiosity and interest, you just need to know and understand that equation. Now, this is where m is the mass, v is the velocity. Thus, if velocity is equal to rate change in displacement over, if it's equal to rate change in displacement, which is simply delta displacement over delta time, it means to say velocity is equal to length over time. But we have got mass. Mass is already a basic physical quantity, so we don't have to worry much. We say Ke is equal to half kg length over time squared. You now put the SI units for length and time we've put for mass already. So we are saying half kg multiplied by m over s squared. And finally, we've got half kg m squared s to the power of -2. Now, your job there, or the simplest thing that you should always do, is to ignore the constant. Any number that has no what can I say, that is known, for example 1, 2, 3, 4, 5, half, and whatnot. If you are looking at equations or SI units or homogeneous equations, those numbers are known as constants. They don't have an unknown term. In other words, that's what you can say, or they are not changing. So you do not need to take note of them. You just ignore them. They are constants. So finally, Ke is equal to kgm squared s -2. I'm not saying that when you are working out kinetic energy, given any figure, and then you ask what is the kinetic energy, I'm not saying that you ignore that half. You put it into practice there. But when you are looking at basic physical quantities or SI units of basic physical quantities, we have to ignore that. So the basic physical quantities that we have there are kg m squared s negative 2, which are similar to those of work. So the SI unit for kinetic energy is also joules. Right, we've got potential energy. It is the energy stored in a stationary body. There are three types of potential energies. We are not going to look at them now. We're going to look at them when we look at kinematics and dynamics and whatnot. Hence, potential energy is called mgh. Again, this is given in your data booklet. You don't need to claim it. You don't need to master that in some sense, but always just try to understand it, of course. So this is where m is the mass in kilograms, g is the acceleration due to gravity in meters per second squared or newtons per kg, h is the height from ground in meters, of course, and then we have acceleration due to gravity. It is measured in newtons per kg or meters per second squared as derived from the equation of weight. We are saying weight is equal to mass times acceleration due to gravity. So when you make acceleration due to gravity, the subject of the formula, you find that it is equal to weight over weight over mass. But weight is measured in newtons. Therefore, we are saying acceleration due to gravity is equal to newtons over kgs, right? So acceleration due to gravity is equal to newton per kg. Or that newton is just the same as saying resultant force. It's a force. Force is measured in newtons, right? And force is measured by a force meter. I hope you know that by now. So we are saying if it's force, it can also be expressed as how we expressed our resultant force back then when we look at the acceleration. We said resultant force is equal to mass times acceleration. Therefore, the SI units for resultant force are kg m s to the power of negative 2. So you can substitute that n with kg m s to the power of negative 2 and then rewrite the equation for acceleration due to gravity. Therefore, g is equal to kg m to the power negative 2 all over kg. You cancel out the kg's and then you find that acceleration due to gravity is also equal to meters per second squared. I move on to the next page. On this page, we are saying that moving on with potential energy, which is equal to mgh, you can simply put the basic quantities there. Pe is equal to kg multiplied by n over kg multiplied by m. Therefore, Pe is equal to Newton meters. But remember, we said that acceleration due to gravity is also equal to meters per second squared. So we can substitute, right? Where we've put n, we can now substitute with kg ms negative 2. Remember, from resultant force. Therefore, that finally will give us, it's multiplied by m, again, the mass, and it will give us kg, by m I mean the meters, sorry. So it's kg m squared s to the power of negative 2. Once again, these are SI units for work. Therefore, the SI units for potential energy, joules. So both kinetic energy and potential energy have mass, length, and time as their basic physical quantities. Moving on to a table which is showing basic physical quantities, we have got 3 columns there. One for basic physical quantities, the other one for measuring instruments, the other one for SI units. For time, we've got a stopwatch as a measuring instrument, and the SI unit for time is seconds. For length, we've got a meter rule as the measuring instrument. The SI unit is meters. M, denoted by letter M. We've got mass. It is measured by a balance, and it is measured in kilograms, denoted by capital letter K, small letter g. Capital letter K for kilo. Light intensity is measured by a photometer, and the SI unit for light intensity is candela, denoted by small letters CD. Amount of matter that contains 6,02 times 10 to the power 23 particles. Has no instrument that measures it. It can only be calculated, and it is calculated and given its answers in moles, denoted by small letters MOL. Temperature, it is measured by a thermometer, and it is measured in kelvins, denoted by capital letter K. Current is measured by an ammeter, and it is measured in amperes, denoted by capital letter A. Now, I could have written charge, right? But I knew initially that it is not a basic physical quantity, but I had to write it so that I illustrate this example. We can't say charge is a basic physical quantity. The reason being that it is not easily measured as compared to current. I know that current is equal to change in rate of flow of charge, right? I know that it's charge over time. But charge can't be measured because it's not as stable as current. We can measure current easily than we can measure charge. Therefore, charge in this case will become a derived physical quantity. I'm going to explain how it becomes a physical quantity in a short while. Now, the SI unit is short for Standard International Unit. SI units are best defined as internationally agreed upon or conventional units for physical quantities, and this is for the purposes of uniformity and consistency. E.g., SI unit for length is meters, not miles or centimeters. Current, voltage, and resistance. Current is the rate of flow of charge. Therefore, current is equal to charge over time. Charge is measured in coulombs or prematurely m seconds. Current is denoted by a capital letter I. Now, back to my initial point where I said charge is not a basic physical quantity, is that we can make it the subject. From current is equal to charge over time, we can say charge is equal to current times time, which gives us the SI units amp seconds. The moment you've got amp seconds, we've got two different base quantities that we've used to make this derived physical quantity. Now, we can say I is equal to Q over T, where Q is time, where Q is charge, and T is time. Moving on to the next page. So we're saying current is equal to coulombs over second. Charge is measured in coulombs, denoted by capital letter C. Time is measured in seconds by small letter s. So we're saying current is equal to C over S. Therefore, 1 coulomb per second is equal to 1 ampere. Voltage is the energy dissipated to move 1 coulomb of charge between 2 points in a closed circuit. Now, voltage is a derived physical quantity. Therefore, to get voltage, we simply need to follow the definition of voltage, which are saying that it is the energy dissipated to move 1 coulomb of charge between 2 points. Energy and charge, that's what we're dealing with. So, voltage is equal to energy over charge. E over Q, where E is energy, Q is charge. Therefore, voltage is equal to joules over coulombs. So finally, SI unit for voltage is 1 joule per coulomb, which is 1 volt. The SI unit is volt there. But joules are identical or similar to kilograms, square meters per second, per square second, and coulombs are identical or similar to amp seconds. Therefore, we can substitute these values for joules and coulombs in our equation for voltage is equal to 1 joule per coulomb. So voltage is now equal to joule per coulomb, which is equal to kg m squared s negative 2 O over as. The SI base units of voltage are equal to kg m squared a to the power of negative 1 s to the power of negative 3 by virtue of that procedure we have taken there. Voltage is mass, length, current, and time as its base physical quantities. Voltage is measured by a voltmeter. Resistance is the impedance to the flow of charge, right? The opposition to the flow of charge. From voltage is equal to current times resistance, which is derived directly from Ohm's law. V is equal to IR, where V is voltage, I is current, R is resistance. You can make R the subject to remain with the V over I. But the SI base units of V and I are kg m squared a to the power of negative 1, s to the power of negative 3, and a respectively. So on the next page now we are saying R is equal to kg m squared a to the power of negative 1, s negative 3 O over a. Therefore, the SI base units of R are equal to kg m squared a negative 2 s negative 3. Resistance is measured in ohms and it is measured by an ohmmeter. Resistance is a derived physical quantity. Scalar and vector quantities. Scalar quantities are physical quantities that have only size or magnitude but no direction, e.g. distance, speed, volume, density, energy, and so forth. Vector quantities are physical quantities that have both magnitude and direction, e.g. displacement, polarization, electric field, and so on. The remarkable difference between scalar and vector quantities, I have shown it in the form of distance and displacement. Distance is a scalar quantity, displacement is a vector quantity. Displacement, remember the definition of displacement is the distance covered in a specified direction, And the definition for distance is the space covered in an unspecified direction. Now, where are we specifying that direction? For distance, we can only say the distance is 5 meters. But for displacement, we say it's 5 meters due east, due west, due north, or due south, right? The following table is illustrating scalars and vectors. We've got scalars on the left hand side, vectors on the right hand side. For scalars, we've got angle, distance, speed, volume, density, energy, mass, time, work, temperature. For vectors, we've got acceleration, force, velocity, electric field, polarization, displacement, linear momentum. Let's look at force as a type of vector. A force is a cohesion or a compulsion that results in a change in direction, shape, or size. If a bag is pulled in two different and or opposite directions, it will eventually move in the direction of the greater force known as the resultant force. We have an example of a bag that is pulled by two different forces that are acting in opposite directions. So we've got 10 newtons to the right, 6 newtons to the left. Now you need to recall that force is measured in newtons and by a force meter. I move on to the next page. Resultant force is equal to the algebraic sum of forces acting on a body. Any force to the left or downwards is always considered to be negative, and the opposite is true. By opposite, I mean any force to the right is positive, any force upwards is also positive. Therefore, resultant force for that diagram is simply plus 10 newtons, and then we are trying to illustrate the algebraic sum. So we need to say plus 10 newtons plus again, isn't it? But now, since the 6 newtons are to the left, they are said to be negative 6 newtons. Therefore, say 10 newtons minus 6 newtons, you get 4 newtons. If the resultant force is positive, it means the body will move either upwards or to the right. But in this case, the bag moves to the right because the resultant force is positive 4. If forces are acting in the same direction, you simply add the forces to get the resultant force, i.e. we've got 4 newtons to the right and also 8 newtons to the right. They add up to get 12 newtons. The length of the drawn lines should always be proportional to their magnitude, or should always be to scale, roughly to scale. A small exercise. Find the resultant forces. We've got 7 newtons acting on the same point as 10 newtons to the right. So what do we do? Simply say plus 10 newtons plus minus 7 newtons, since they're to the left. Plus 10 newtons minus 7 newtons, you get plus 3 newtons. Now those forces are also known as coplanar forces. The definition for coplanar forces is simply that these are forces that are acting at the same point. As you can see, 10 newtons are pulling from the same point as 7 newtons are also pulling. So these are coplanar forces. We've got 3 newtons and 6 newtons acting in the same direction. We've got the resultant force being equal to plus 9 newtons. Vector forces acting at an angle. We've got a situation: a 50 kg bag of cement is pulled by two different angles acting at 45 degrees to each other as shown below. So I've tried to show that there are those, let's say, ropes that are pulling that bag, one being 60 newtons, the other one being 50 newtons. The clue there is that you should redraw the coplanar forces, right? When you redraw them, they make something like that. This force is at an angle. You are told at a 45 degree angle, so you draw it like that. Now you draw parallel lines to these forces, right? The force OA and the force OC. Draw parallel lines to it. Line AB is parallel to 50 newtons, or the 50 newton line or vector. Line BC is parallel to the 60 newton vector. The second clue now is that you should draw a diagonal from D to B as shown on the next page. Now on this page, I've tried to draw a diagonal like that, and then that diagonal will be our resulting force in every case. So you should always be in a position to draw that as accurate as you can. The resulting force, not technically accurate, but just as presentable as it can be. So I've drawn that resultant force and I've tried to show it at my best. Now that diagonal is the resultant force, as I just have mentioned. Always use the format to calculate that resultant force. You always use the format R is equal to R squared is equal to F1 squared plus F2 squared minus open bracket 2 multiplied by F1 multiplied by F2 multiplied by cos theta close bracket. where R is the resulting force, F1 and F2 are the forces or the coplanar forces, theta is the supplement to the given angle. To find the supplement of the given angle, you say 180 minus the given angle. In this case, theta is equal to 180 minus 45, you get 135. Therefore, R squared is equal to 50 Newton squared plus 60 Newton squared plus 2 times 50 Newton times 60 newtons times cos 135 degrees. When you are working out physics problems, you should always put the units. If you don't put the units, you won't be able to get a mark there. On the following page, you are saying R is therefore continues to be worked out. We get R is equal to root of 50 Newton squared plus 60 Newton squared minus 2 multiplied by 60 multiplied by 50 Newton multiplied by 60 Newtons multiplied by cos 135 degrees. Therefore, R is equal to 101,69877426557. R is therefore finally equal to 102 Newtons to the nearest whole number. Since our raw values are to the nearest whole number, we look at our raw values 50 Newtons, 60 Newtons and 135 degrees. They are all expressed to the nearest whole number. This method applies to all forces that are not acting at 90 degrees to each other. Method emanates from the cosine rule, so I would give you, or I would dare you to go look at the cosine rule for you to understand this better. If the forces are acting at 90 degree angles, you use the Pythagoras theorem to get the resultant force as shown below. We've got forces acting at right angles, 60 newtons and 50 newtons, having their heads at A and B. Your first job there is to join the heads of the vectors and draw a diagonal. Remember, the diagonal is drawn from the tails of the vectors. The tails of the vectors intersect at that 90 degree angle. So when you draw a diagonal, you get your R, and then you say R squared is equal to F1 squared plus F2 squared. This is for angles that are acting at 90 degrees to each other. You say R squared is equal to 50 Newton squared plus 60 Newton squared. R is equal to root of 50 Newton squared plus 60 Newton squared, which is R is equal to 78,102,496,759,065. You express that to the nearest one whole number, which is because that our raw values were given to the nearest whole number. Thank you very much for attending this lesson. The core prize that I had for you is an A at your subject, a pass, a straight pass. An A plus is what I am offering on a silver platter. Don't forget to subscribe to my channel and don't go anywhere without sharing this video with friends and family. Have a good day.